Hello students, welcome to EPG Pathshala and I am Reema Gupta from University of Delhi. Today we are going to talk on module Quantum Dot Preparation through Colloidal Methods 1 and it is under the paper at Nanoscience and Nanotechnology 1. So after completing this module, the students will be able to learn about the basics of colloids. They will be able to know the classifications of colloids under different categories and more important, the interaction between the particles. So before moving to colloidal, let's discuss about the quantum dot preparations. Unfortunately, most quantum dots are toxic, which implies a potential danger, especially for future medical applications. So, the most widely used and studied quantum dots consist of a core of cadmium selenide or telluride because their quantum confinement region spans the entire optical spectrum. It is reported that the cadmium ions were determined as a primary cause of cytotoxicity because they are able to bind the thiol groups on critical molecules in the mitochondria and cause enough stress and damage to cause significant cell death. However, the release of cadmium ion, that is CD2 plus, could be reduced or eliminated by adding artificial or additional surface coatings. So scientists in Ireland have been using gelatin during the production of cadmium telluride quantum dots, thereby reducing the toxicity of the particles. It is reported that the peptides could be used as excellent ligand for coating the surface of quantum dots for several reasons. The first is the peptide mimic the biological environment and are stable at physiological pH levels. The second is reactive groups, that is amines, carboxyls, thiols and even peptide tags can be disabled or dilate into the hydrophilic domain of the peptide sequence and enable enzymatic or standard conjugation chemistry. And the third one is molecular evolution strategies. To randomize, the peptides can be adapted to select high affinity binders to the quantum dot surface. And the next is there is possibility of creating the multifunctional quantum dots by mixing peptide sequence in certain molar ratios. So for the example, the quantum dot with biotin and PEG conjugating receptors, ligand and PEG, etc. So apart from this, the quantum dot preparation can be done using colloidal solutions, so which we will be discussing in detail in this module. What is colloid? Let's know the basic of colloid. A colloid is a mixture which contains microscopic dispersion of insoluble particles suspended in a solvent. In some cases, the dispersed material itself is termed as colloid and the mixture containing this material suspended in a solvent is termed as colloidal suspension. A colloid is different from a solution. In a solution, solute and solvent constitute the same phase. A colloid has a dispersed phase, that is suspended particles, and a continuous phase, that is suspended medium. A mixture can be termed as a colloid if it does not settle or takes a very long time to settle. So for example, milk is an emulsified colloid of liquid of butterfat globules dispersed within a water-based solution, and the photograph is shown here. The dispersed phase can range from 1 to 1000 nanometer, and these particles are easily observable under an optical microscope. However, for small sized particles, that is diameter less than 500 nanometers, an electron microscope is necessary. The homogeneous mixtures having dispersed phase of such dimensions is usually termed as colloid aerosols, emulsions, foams, dispersions, or hydrosols. The surface chemistry directly affects the dispersed phase particles. Some colloid may either be translucent, that is, because of Tyndall effect, or opaque or slightly colored. The study of colloidal suspension comes under interface and the colloid science and the field that was formally introduced by Thomas Graham in 1861. Classification of colloids. It is usually difficult to measure the size of the dispersed particles. Additionally, the colloids appear much like solutions, and for these two reasons, colloids are classified and characterized by their physiochemical or as well as transport behaviors. For instance, if a colloid consisting of solid phase dispersed in a liquid is passed through a membrane, the solid particles do not diffuse across the membrane, while in a true solution, the dissolved ions or any molecules also diffuse through the membrane. So, due to size exclusion, the particles of a colloid do not pass through the pores of ultrafine membranes having pores diameters smaller than the diameter of the dispersed particles. As the size of the pores of the membrane is decreased, the concentration of colloid particles present in the filtered liquid also decreased. Thus, the measured concentration of a truly dissolved species depends upon the experimental conditions used to separate the dispersed state from the liquid. This has applications in solubility studies of readily hydrolyzed molecules, example aluminium, that is Al. So students, we can say that based on the nature of interaction between the dispersed phase and dispersed medium, colloids can be classified as hydrophilic colloids and hydrophobic colloids. So in hydrophilic colloids, there are water-loving colloids. So the colloid particles are attracted towards the water and they are called reversible sol. Whereas in hydrophobic colloids, these are opposite in nature to hydrophilic colloids. So the colloid particles are separated or repelled by water. They are also called irreversible sol. In some cases, the colloidal suspension be considered a homogeneous mixture. This is because the distinction between dissolved and particulate matter can be sometimes a matter of approach which affects whether or not it is homogeneous or heterogeneous. The colloidal solution are classified on the basis of medium or phase. So, the medium or phase for the dispersion medium and dispersed phase can be gas, liquid or solid. So, if the dispersed phase is gas and dispersion medium is gas, then no such colloid known or it cannot be formed. Whereas, when the dispersed phase is liquid and dispersed medium is gas, then it is liquid aerosol. for example, fog or clouds, and so on. Similarly, when the dispersed phase is solid and medium is gas, then it is called solid aerosol. So, if we talk about liquid as dispersion medium, the dispersed phase can be gas, liquid, or solid. So, according to it, if it is gas, then the examples are foam, cream, and so on. If the phase is liquid, then it is emulsion, and if it is solid, it is called sol. The dispersion medium is solid, then the dispersed phase can be gas, liquid, and solid. So it can take solid form, gel, or solid sol, respectively. Interaction between particles. The following forces play an important role in the interaction of colloid particles. The first is excluded volume repulsion. So, this refers to the impossibility of any overlap between hard particles. The second is electrostatic interaction. Usually, the colloid particles carry electrical charges. This causes attractive or repulsive Coulombic interaction among particles. These interactions are affected by the charges of both the dispersed phase and dispersed medium, and also on the mobility of these phases. The third is the third is entropic forces. So according to second law of thermodynamics, a system progresses to a state in which the entropy is maximized. This can result in effective forces even between hard spheres. The next interaction is van der Waals forces. This occurs because of the interaction between two dipoles, which may be either permanent or induced. Although the colloid particles do not have permanent dipoles, any variations in electronic density may cause temporary dipoles in the particles. A temporary dipoles in one particle can induce dipole in the nearby particles as well. So both these dipoles, that is temporary and induced, are attracted towards each other owing to the van der Waals forces. These forces are always present unless the dispersed and continuous phases have same refractive index. These forces are short range and are attractive. The next force is steric force. These forces modulate the interparticle forces between polymer coated surface or in solutions having a non-adsorbing polymer. They result in either steric repulsive forces, that is mostly of entropic origin, or attractive depletion forces between them. These effects are of high importance in superplasticizers, wherein they can boost the workability of concrete and also reduce water content. Now comes colloidal preparation. There are two principal ways of preparing the colloids. The first is dispersion of large particles or droplets to the colloidal dimensions by milling, spraying, or application of shear, example shaking, mixing, or high shear mixing. The second is condensation of small dispersed or small dissolved molecules into large colloidal particles by precipitation, condensation, or redox reaction. Such processes are used in the preparation of colloidal silica or gold. Stabilization or peptidization. Students, you can see an example of stable and unstable colloid dispersion. So let's discuss it. The stability of colloid suspension is measured by the ability of particles to remain suspended in the solution under equilibrium condition. So this figure shows the schematic representation of stable and unstable colloids. The stabilization is hindered by aggregation and sedimentation phenomena, which are driven by the colloid's tendency to reduce the surface energy, reducing interfacial tension while stabilizing the colloidal systems by reducing this driving force. The aggregation is due to the sum of interaction between the particles. So, if the attractive forces such as van der Waals forces prevail over the repulsive ones, which is electrostatic force, then particles aggregate in clusters. Electrostatic stabilization and steric stabilization are the two main mechanisms for stabilization against aggregation. So, the electrostatic stabilization is based on the mutual repulsion of like electrical charges. In general, the different phases have different charge affinities, so that an electrical double layer forms an interface. So small particle size lead to enormous surface areas, and this effect is greatly amplified in colloids. In a stable colloid, mass of a dispersed phase is so low that its buoyancy or kinetic energy is too weak to overcome the electrostatic repulsion between charge layers of the dispersing phases. So the steric stabilization consists in covering the particles in polymers, which prevents the particles to get close in the range of attractive forces. The gel network stabilization represents the principal way to produce colloids stable to both aggregation and sedimentation. The method consists in adding to the colloidal suspension a polymer able to form a gel network and characterized by shear thinning of properties. So example of such substance are xanthan and gargum. So students, you can see a figure showing the comparison between the steric and the gel network stabilization mechanism. So the left figure shows the steric stabilization, which shows the liquid phase in water, whereas on the right hand side it shows the dispersion in a gel network. The particles settling is hindered by the stiffness of polymeric matrix, where particles are trapped, and in addition the long polymeric chain can provide a steric or electrosteric stabilization to dispersed particles. The rheological shear thinning properties find beneficial in the preparation of the suspensions and in their use, as the reduced viscosity at high shear rates facilitates deagglomerations, mixing, and in general the flow of the suspension. Now comes destabilization. In unstable colloids, the particles aggregate and forms cluster owing to the interparticle attractive forces. This property of colloids can be used to produce photonic glasses, and the following methods can be employed to achieve this. So the first is the removing of electrostatic barrier that prevents aggregation of the particles. This can be accomplished by the addition of salt in a suspension or changing the pH of a suspension to effectively neutralize or screen the surface charge of the particle in suspensions. This removes the repulsive forces that keeps colloidal particles separate and allow for coagulation due to van der Waals forces. The addition of a charged polymer flocculate and the polymer flocculants can bridge individual colloid particles by attractive electrostatic interaction. For example, negatively charged colloid silica or clay particles can be flocculated by the addition of a positively charged polymer. The next is the addition of non-adsorbed polymer called duplicants that cause aggregation of the particles due to entropic effects. The next is physical deformation of particles, example stretching. This may increase the van der Waals forces more than the stabilization forces such as electrostatic, resulting in coagulation of colloids at certain orientations. So, unstable colloid suspensions of low volume fractions form clustered liquid suspensions, while the individual clusters of particles fall onto the bottom of the suspension or float to the top if the particles are less dense than the suspended media. Once the clusters are of sufficient size, of the Brownian forces that work to keep the particles in suspension be overcome by the gravitational forces. However, the colloid suspension of higher volume fraction form colloidal gels with viscosities properties, whereas viscoelastic properties or viscoelastic colloid gels such as bentonite and toothpaste flow like liquid under shear but maintain their shape when shear is removed. It is for this reason that the toothpaste can be squeezed from the toothpaste tube but stays on the toothbrush after it is applied. Now, the next topic is monitoring stability. Multiple light scattering coupled with vertical scanning is the most widely used technique to monitor the dispersion state of a product, hence identifying and quantifying destabilization phenomena. It works on concentrated dispersion without dilution. So when liquid is sent through the sample, it is backscattered by the particle or droplet. The backscattering intensity is directly proportional to the size and volume fraction of the dispersed phase. Therefore, the local changes in concentration, example, creaming and sedimentation, and global changes in size, example, flocculation, coalescence, are detected and monitored. So, students, this figure shows the measurement principle of multiple light scattering coupled with vertical scanning. Accelerating methods for shelf life prediction. So, in this, the kinetic process of destabilization can be rather long, up to several months or even years for some products, and it is often required for the formulator to use further accelerating methods in order to reach reasonable development time for new product designs. So, the thermal methods are the most commonly used and consist in increasing temperature to accelerate destabilization below critical temperatures of phase inversion or chemical degradation. So, the temperature affects not only the viscosity but also interfacial tension in the case of non-toxic surfactants, or more generally the interaction forces inside the system. So, storing a dispersion in high temperature enables to stimulate real life conditions for a product. Example, tube for sunscreen creams in a car in the summer, but also to accelerate destabilization processes up to 200 times the mechanical acceleration, including vibrations, centrifugations, and agitations are sometimes used. They subject the product to different forces that pushes the particles or droplets against one another, hence helping in film drainage. However, some emulsions would never coalesce in normal gravity, while they do under artificial gravity. Moreover, segregation of different pollutions. Moreover, segregation of different populations of particles have been highlighted when using centrifugation and vibrations. Colloidal crystals. A colloidal crystal is a highly ordered array of particles that can be formed over a very long range, typically on the order of few millimeters or to the centimeters, and that appear analogous to their atomic or molecular counterparts. So, one of the finest natural example of this ordering phenomena can be found in precious opals, in which brilliant region of pure spectral color results from closed packed domains of amorphous colloidal spheres of silicon dioxide. So, it has been known for many years that due to repulsive Coulombic interaction, electrically charged molecules in an aqueous environment can exhibit long range crystals like correlation with interparticle suspension distances, often being considerably greater than the individual particle diameter. The periodic arrays of submicrometer spherical particles provide similar array of interstitial voids that act as natural diffraction. So, it is natural diffraction grating for visible light waves, particularly when the interstitial spacing is of the order of magnitude as the incident light wave. So, in order of these cases in nature, the same brilliant iridescence or the play of colors can be attributed to the diffraction and constructive interference of visible light waves, and that satisfies the Bragg's law in a matter analogous to scattering of X-rays in crystalline solids. So, the large number of experiments exploring the physica and chemistry of these so called colloidal crystals has emerged as a result of relative simple method that have involved in 20 years of preparing synthetic monodisperse colloids in the last years, and through various mechanisms implementing and preserving their long range order formation. So, students, let us now summarize what we have learned in this module. So, first we discussed about a colloid. So, what is a colloid? A colloid is a mixture that contains a microscopic dispersions of insoluble particles suspended in a solvent. In some cases, the dispersed material itself is termed as colloid, and the mixture containing this material suspended in a solvent is termed as colloidal suspension. So, on the basis of the interactions between the dispersed phase and the dispersion medium, the colloidal solution are further divided into hydrophilic and hydrophilic colloids. So hydrophilic colloids are water-loving, where the particles of the colloids are attracted to the water, whereas hydrophobic do not attract the water. So these are also termed as reversible sols, which are hydrophilic. Hydrophobic sols, on the other hand, we discussed, are not water loving, and there is repulsion or repulsive interaction between the particles of the colloid and the water. So these are irreversible sols. The most popular methods to prepare the colloids we have discussed in this module, and these are: first is dispensing large particles to colloid dimensions through milling or mixing. The second is condensing very fine particles to produce larger colloid particles through precipitation, condensation, and so on. So, this approach is very frequently used to prepare the colloids of silica and gold. So, the destabilization process can be rather long, on the order of few months to years. Therefore, certain accelerating techniques can be used to reduce the development time for designing new products. So, among these techniques, the thermal processes are most common and involve increasing the temperature to accelerate destabilization. However, the temperature is kept below the critical temperature of phase inversion or chemical degradation. Thank you.